Okay, so for lab number one, let me make a few clarifications. We were talking about the differences between isoosmotic and isotonic and how certain types of solutions may be isoosmotic but not isotonic. You should know the differences between those terms and understand the relationship between water movement across the cell membrane and the effects that that has, in our case, on red blood cells. So the confusing part was people were asking whether or not they needed to do a write-up. You don't need to do a write-up for this lab because you weren't here to actually see all the components. And in fact, there were two components that we couldn't do because we needed a class group in order to make that happen. And so just fill out the questions that are on the sheet that we handed out to the best of your ability and turn those in. As far as when you turn those in, I need to have them all by the end of the semester for sure, so the more efficient you are and the more fast you are filling that out, send it to me. That saves me a lot of work that I don't have to do it again. Okay, today we're going to shift gears a little bit and we're going to talk about metabolic rates. Turns out that when you're looking at animals across the spectrum, the most complex equations that we have and the most complex processes that are ongoing on planet Earth are animal physiology, whole animal physiology responses. These are the most complex types of reactions that we see in the entire universe. So beyond that point, as you move to levels higher than single organisms, or if you move to lower levels of parts of organisms, the complexity decreases logarithmically, as it turns out. So being able to understand how animals work and come up with what we would like to think of as something along the lines of a unifying theory in biology. That theory, although we haven't worked out all the details yet, that theory will be metabolic. Okay, so that's how animals use energy, and that's what we're going to spend the next couple of weeks talking about different ways that we can measure that, and there's lots of different variations on it as well. Today we're going to start with an older technology, and yet probably one of the most precise technologies that we have, working with Gilson Respirometry. Gilson was a scientist back in the 1940s who came up with the idea that we can use the ideal gas law, and you would remember that. It's P equals T. Okay, in which case we're looking at pressure.
Hey Doc, let's use a darker Sharpie if we can.
So the equation P V equals T, okay, where pressure is P, volume is V, the ideal gas constant, the ideal gas constant along with absolute temperature. Okay, so we're using that. This particular equation. It turns out that most of the other types of systems that we're going to talk about are not based in the laws of physics. Okay, in other words, we still have physical reactions that go on, but you can't define them using a physical equation like we can here. And so that makes this one especially useful for teeny tiny little things. For example, we can measure the metabolic rate on a fish egg over the course of several weeks or several months if necessary. And so this particular equation then represents how we're going to use the Gilson respirometer. And the idea is we are going to hold two of these units then are going to remain constant, and that's going to be the volume of the vessel that the cricket is in, number one, and the temperature at which we hold it, number two. Okay, so these two variables remain the same. That means the only thing that can change is pressure. And pressure will be proportional to oxygen uptake in our case. So let me go ahead and draw you a schematic to begin with that might help you visualize how this works. I'm going to simplify this. In a moment we'll look at the Gilson respirometer directly and we'll be able to equate all the components equation and to the drawing that I'm going to give you. So basically the idea is we hold the volume constant, and because the volume is made up inside of a glass vessel, it doesn't matter it's a sealed glass vessel, so the volume can't change. The volume is constant. And then the second thing, of course, that we have is temperature, and we'll talk about that here in a moment. So we start with two different vessels. Okay, right here, and there's a little sidearm that comes off of the vessel. So here's the vessel that we're going to use to compare control, basically, to our reaction. Okay, so we have two of these that are set up. One of them is going to be a reaction flask. The reaction flask then will contain the animal. That's where all the oxygen is going to be absorbed, and the CO2 also is going to be picked up. So within the reaction flask then, we're going to go ahead and we're going to use crickets. And so we're going to put a cricket in the reaction flask here, and it's going to pick up oxygen. Now, this little sidearm that you see here is actually, it's got a little vent associated with it. I'll show you one of those here in a moment. A little vent that comes up there as well. And we can go ahead and vent the animal to the atmosphere so that while we're waiting for the temperature to change perhaps, or if we're just setting up the system altogether, we can go ahead and open the vent, and that will allow the insect to have access to the outside atmosphere. This reaction flask then is going to be, go ahead and this part right here, it's going to be connected to a manometer tube. We're all familiar with manometers, I'm pretty sure by now. Okay, so the manometer tube's going to move in this direction, and it's going to be connected to a reference flask. The reference is, you can think of that like our control. Okay, so here's the reference flask, and this one is a beam sidearm. Okay, so the idea is right now we've got our cricket inside the reaction flask. It's open to the atmosphere. We can turn this vent, and when we get ready to do it, we'll show you how that works. We'll turn the vent. That will close this system. Okay, so now, as the insect withdraws oxygen, so it's going to pick up oxygen, that's going to lower the total number of gas particles inside the reaction flask, which is going to drop, it's going to create a negative pressure. So we're going to see a movement then. This is our manometer fluid level initially when they're open to atmosphere. If we close them off from the atmosphere, we'll see that the manometer fluid will start to climb up the tube. Okay, and so our job then is to watch that, and then we monitor how much that comes in. Now the other thing that happens in the Gilson respirometry, you can run them like this, but it's tedious because you have to take them out frequently and do some other kinds of work. So Gilson's advent was the fact that he went ahead and hooked up a gas type system. I'm going to put it up here. It's essentially a modified syringe, and I'm going to draw it like it's a syringe, but it'll look a little different when you see it on the unit. And so as that pressure drops here and pulls the manometer tube on the insect side, pulls that fluid upward, we can go ahead and have this plunger, and it's calibrated in microliters. Okay, so we have microliters, and for our purposes, and you can use it if you build your own, which is relatively easy to build your own, you can just use a regular gas type syringe. But on the Gilson respirometer, it's set up in such a way that we can just rotate the plunger it's on a threaded rod, and it's also geared in such a way that we can measure directly from the change in numbers that we'll see looking at the syringe. It'll tell us exactly how many microliters were absorbed per unit time. So we will pick up the time component later and talk about that, because we're going to want to get our respiratory rate in microliters per minute or per hour, whatever the case may be, relative to units, that is, we can go ahead and measure very precisely then how much oxygen is being picked up. And the relationship between oxygen uptake is indirectly correlated then to calories. So there are ways for us to take basically a cheat sheet where we can pull up what we call the isocaloric values, and we can convert oxygen consumption into heat, which is measured in calories, and ultimately then we can convert all of the numbers to calories burned. Okay, and that's the total energy that the animal's using at any given moment in time. The nice thing about that is we can go ahead and manipulate the environment that the insect is in to do various experiments to see how they respond to changes in environmental conditions. So, again, this is the reaction, this is the reference class, and we will let this run. What we'll do is we'll measure probably in 5 to 10 minute intervals. We will look at, we'll adjust the syringe, and so we will have a reading at every 10 to 15 minutes for maybe a half hour, maybe 40 minutes, and we will go ahead and be able to utilize those numbers then to get an average oxygen uptake for crickets of a certain body mass. Okay, so that's our first job. Once we get the first set of numbers collected at room temperature, we'll go ahead and increase the temperature, and we'll see how metabolism is affected by an increase in temperature. Now, when we go ahead and raise that temperature, there's a formula that we can use then to calculate a number called the temperature quotient. It was first described by Jacobus van Hoff, who won the first Nobel Prize in 1901, and so he's pretty famous for a lot of things, this particular equation as well, although that's not what he won the Nobel Prize for. He was a botanist originally, but he was pretty interested in respiration and photosynthesis and that kind of thing, and so he did a lot of work in that area and came up with this equation where we have the oxygen uptake, and we usually give that a V with a dot and an O2. When you see the dot above one of those units, it means over time, so this is a rate. Okay, so this is the rate of oxygen consumption. Okay, so we're going to measure the VO2 at room temperature, and then we can go ahead and we can increase the temperature, and then we run the experiment again. Okay, now with an increased temperature, ectotherms will show an increase in their overall oxygen uptake. Okay, now for you and I, that's not true because we're homeotherms. We always are the same temperature, so it's not a problem for us. But for insects, that's a big deal. And what we're going to look at is an acute change, or look for an acute change in the uptake of oxygen over time. And we can go ahead and calculate that as a ratio. And so we have V2, which is our VO2. Let me go ahead and put that down there. So our uptake at time 2 divided by our uptake at time 1. Okay, so this is after we added the heat. We divide that by VO2 at room temp, and we can go ahead and take this equation becomes, let's see if I can remember this now, 10 divided by temperature 2 minus temperature 1. Okay, that's an exponent. And so this equation then will give us this will give us this is time 2, this is time 2 and time 1. But there it is. So these things then will give us it's a relatively simple equation. Now, if your temperature is exactly 10 degrees apart, this drops off and you just divide the two and you're left with just this component. And so you can just divide it. But 10 degrees centigrade is a lot of temperature to move an animal up, and we don't want to shock the animal. We don't want to have any problems with the animal, dying on study because we increased, you gave it too much temperature. And so typically we use something a little less. We'll probably use 5 or 6 degrees on the crickets. Okay, let's take a break. We'll run over and set up the Gilson, and we'll show you what that looks like. Okay, so this is the Gilson respirometer, and you can see here are our syringes. You can see the numbers that are associated with each of these dials, and they are calibrated to microliters. We always start out at 100 microliters because it's possible that during the course of the study, things may run backwards a little bit, and so we always leave a little bit of room before you begin to see the stabilized kinds of responses that we're looking for. So each one of these syringes then is associated with each one of these channels. Each one of these channels will contain a vessel with a cricket in it, and that's our goal next, is to put those in there. So as we go through the process, a couple of other things. We will heat the animals eventually, in which case we've got a temperature controller that will set at about 6 degrees above room temp, which is, I'm going to say, probably going to be 32 or so. And that shouldn't bother the crickets any, but it will tweak their metabolic rate, so you'll be able to calculate a Q10 value for that particular experiment. Now the Q10 value is a really worthwhile thing to have because it tells you how sensitive the animal's metabolic rate is to temperature change. And again, this is one of the most fundamental types of studies that we do in biology, and if you go on to be a biologist of any type, you will run across this, not necessarily this particular method, but you'll run across metabolism and metabolic numbers a lot, and so you need to be aware of that. Okay, so what we're going to do then is, here's our reference flask, and it's down here, and it's a common flask, so it's attached so that all of the flasks are attached to it. I'm not going to take it out of the water because it'll change the temperature, and we've been waiting for that to stabilize for the last half hour or so. So we're going to keep the reference flask here. Each one of the reaction flasks then will have a cricket in it, and we will go ahead and start putting those together. Meanwhile, we also have a valve here that allows me to either open or close. This is a gas valve. Now, ordinarily for our purposes, we leave it open and just close it once we begin the study. It's useful because, you might wonder why we even have it here, but it's useful because we can, if we're working with, say, plants, we can put CO2 through this, right, run through the system. So you can change the gas concentration. So for example, maybe we want to see how crickets respond metabolically if they're hypoxic, right? And so we could run a atmosphere through the system where it was maybe 5% of the normal oxygen concentration, 10%, 20%, and do an experiment that way if we decided we needed to do so. Okay, so let's go ahead and we'll get started. Here's our crickets. We got a whole bunch of them in there, and you can see this is just a common field cricket, nothing really special about them. And we'll prep the flasks one at a time. So here's the flasks. They are made out of just 100% glass. There's a ground glass joint on each of these where we're going to join up the flask to the intake here on this glass seal. And we will put in the sidearm, we're going to add a little bit of sodium hydroxide. Now we're going to go ahead and add just enough sodium hydroxide to saturate a little bit of Wattman paper so that it's not floating in sodium hydroxide. It's about a 10% solution, sodium hydroxide, and that's going to pick up the CO2. So the only thing that's going to change is the oxygen concentration inside this flask. All the CO2 has been picked up. It's a sealed system once we go ahead and flip all the levers in the right direction. Okay, so let's go ahead and I'll prep one of these so that you can see how this works. This is the vent that we talked about, and when the vent is placed into the, we usually have them facing in this direction, and when you've got the blue spur that's pointed forward toward the CO2 chamber, or the sodium hydroxide chamber, once you turn it this way, the animal still picks up oxygen from the top in this opening, and it comes out here into the sidearm. And so they're open to atmosphere. When we start the experiment, we will turn all of these at 45 degrees, and that will seal the system at this end. When we flip down the gas valve, that seals the system at the other end, and then to start the studies, we simply, once everything's in place, we simply push these 4 levers down, and everything goes. Okay, so let's go through the technique here, because you can't do it yourself, but I can do my best to show you how that works. So here's our Wattman paper, just regular old absorptive paper that we might use for other purposes, and our sodium hydroxide. There's a tiny little bit of it that we mix up here because we don't need anything but more than a drop, and we will put that into the sidearm and add a drop of sodium hydroxide. There we go. Okay. I always like to push these papers down a ways so that the crickets can't stick their little heads in, because for some reason they will eat the sodium hydroxide and it will kill them during the study, and we don't want that to happen. Next thing we do is we get some stopcock grease. You will use this if you use vacuum in any of your chemistry classes and things like that. Okay, and we take the vent, being really careful that we don't plug up that little hole, because of course while they're breathing atmospheric gas, that hole needs to be open. So put a little bit of stopcock grease around that. We avoid that little hole, and we can stick this into the sidearm. You want to roll it all the way around once or twice to make sure that it's all hooked up good. There we go. And now we're ready for the cricket. Now for the cricket, I'm going to get a little bit of DI water. And we'll add a drop of the DI water to the bottom so that the animal doesn't dry out, maybe a couple of drops. Okay, next, we get these connectors here, the glass connectors, and we're going to smush a little bit of stopcock grease on this, and a little bit on the inside also of the reaction flask. And then we get to go after the crickets. Put the cricket into the reaction flask, and then we put the reaction flask on the ground glass adapter. Move that around back and forth so we're not going to get any leaks. And then we're going to go ahead and secure that with a rubber band. Okay, so cricket number 4 is in there. You can see the blue spur is facing outward, so it's receiving atmospheric gas. And of course, here's back here on the back are where the manometers are. Okay, and so everything's hooked up through tubes to the manometer, to the cricket vessel, okay, or our reaction vessel. Okay, now we're going to want to keep them all at the same temperature. So when we're set like this, we can lower this into the water bath. And that's an airtight seal with the stopcock grease on it. And so we'll let the cricket acclimate then a little bit to the temperature in the water bath. So right now our temperature in the water bath looks to me to be 21.5 right now. So let me go ahead and put that on the board. So T1, 21.5, 21.5 degrees. So we're going to need that number when we calculate the T10. Okay, so we're going to turn this off for just a minute while we go ahead and put the rest of the crickets into the flasks, and then we'll connect back up so you can see what it looks like when it's all ready to run. Okay, so you can see now that all of the crickets have been placed into their corresponding reference or reaction flasks. They're all submerged in a water bath, and that's going to hold the temperature constant. The water bath then is controlled by this thermostat unit, and it keeps the temperature within about 0.3 to 0.5 degrees of their set point temperature, okay, which is 23 degrees. So that'll be our starting temperature for this particular part of the experiment. After we've collected data, we haven't started this trial just yet, but once we start the trial, we will collect data for about 30 minutes to 40 minutes until we get some good numbers. And once we've got that, then we'll go ahead and change the temperature. We'll increase it by about 6 degrees, and we'll repeat the entire experiment with the same crickets. That'll give us the opportunity then to go ahead and calculate their metabolic rate and also to calculate the metabolic sensitivity to temperature. So I'm going to go ahead and start this. Now I'm going to take each one of these flasks that contains a cricket, and I'm going to turn the blue pin away from the front position, and that's going to seal the jar. And then we will start the experiment by pushing these 4 levers down simultaneously, and we'll start also the timer. Okay, so we should have, do we have a stopwatch? Probably not.
Can you use my phone?
Okay, so we're going to go ahead and set the timer, and we will take measures every 5 minutes over the next roughly 40 minutes. So here's how we're going to go. All the crickets are sealed off now to the outside. We're going to close the gas valve, and we'll start the procedure. Okay, so we have completed the first section where we measured metabolic rates in crickets at room temperature. So our next goal then is to look at metabolic sensitivity, or Q10 responses of crickets. And we're going to do that right now. We're going to reset the system. During the first trial, we had a couple of the crickets stuck their head into the side arm, and they picked up some
Can kind of show you that
picked
there.
up a little bit of potassium hydroxide, which is enough to put them to sleep. So we still have 2 crickets that are active and ongoing, and we might have a third one, but we're going to try channel 1 more time.
Okay.
But we're going to go ahead and set the temperature now is at 29 degrees centigrade, so we moved it up from the original temperature. And what we would expect is to see that the animals' metabolic rates would increase. In most cases, those metabolic rates would double. And so we refer to this then as Van Hoff's rule. In most cases, ectotherms that experience a temperature degree or a temperature change of 10 degrees centigrade can expect to double their metabolic rates. So we're going to go ahead and close off the valve. There we go. So the gas valve is off. Everything's connected. We've reset all of the numbers that we're going to use anyway to 100 again. And we will go ahead and seal off the vents and start the process. We will collect the data, and we'll get back with you as soon as we're done.
And just so you see the data, we have written it on the board. We will be sending you guys a data sheet after this is all done, so if you can't see it all that well, that's totally fine, but just showing the M1 did not work. There was a leak in the system. M2 that was the cricket that had that issue with those chemicals, and then 3 and 4 are our healthy crickets. But we will be looking at M3 and M4 for this current trial. But again, you'll be getting that data sheet in your email with the assignment, so don't worry about if you can't see it all that well.
Okay, so you have we have successfully completed together the first metabolic measurement that you would make. Now, if you're going to be a real biologist, it won't be the last one you make. There is a good opportunity here for you to start to understand a little bit more about how we use these data. And so we put together some information on the board that we've collected as we've done this experiment. And we will go ahead and transfer this onto a spreadsheet so that you'll be able to use it. But just to give you an idea of what I'm going to need from you, number one, for you to be able to explain the Gilson methodology. Don't forget about the theory that we have, that it's based on the ideal gas law and all of the components that go into that, which makes it a highly accurate way to measure metabolic rates. We will then ask you to calculate the change in microliters between measurement intervals. So from the first interval to the second interval, calculate that difference. The second to the third, calculate that difference in metabolic rate. And then take those measures when you get to the end, add them all together and divide through to get an average and a standard deviation. Okay, so that you'll have the data on how crickets responded to oxygen uptake in the crickets, how they responded with oxygen uptake. So after you've got the first data set done at a cooler temperature, we'll go to the higher temperature and do the exact same thing. And you'll have two averages then that you can use in the temperature quotient equation. It'll also be on the sheet that you can look at, or you can just look it up online. But you'll be able to go ahead and calculate then the temperature quotient. Keep in mind that the temperature quotient then is a really important number. It's the thing that we look at in terms of, at least for ectotherms, how they change their metabolic rate related to the temperature in their environment. And what we'll see is that some animals change quite a lot, other animals don't. Now this only works for ectothermic animals, right? We don't do this for homeotherms because we're at constant temperature all the time. But for ectotherms, you can change the temperature and then make some comments on your report about how the temperatures, or how the number of values changed as you went from a lower to a higher temperature. That's metabolic sensitivity or the temperature quotient. That's the number that will tip you off as to how those animals respond. Take some time, think about those kinds of things. If you have questions, write to Taylor or myself, and we will try to address those. And we'll go ahead, Tyler, not Taylor, sorry. So we will go ahead and be happy to help you with any questions that you may have. So we're not entirely certain what our next week's exercise is going to be, but we will